So the last topic in this section is multiplicative inverses, or matrix inverses. The idea here is that we now know that the diagonal ones matrix is the multiplicative identity of ordinary numbers, and something that's often useful in ordinary numbers is being able to divide by a number. And that's the same thing as multiplying by its inverse. So notice that if we were talking about scalars, if I wanted to divide by a 7, that's the same thing as multiplying by a 1/7, and 1/7 is called the multiplicative inverse of 7. So in some sense, the multiplicative inverse is just what divides by a number in order to get us back to the identity. And notice that you could write this 1/7 as a 7 to the negative first power. In correspondence with that, we're going to use the same notation for matrices. With matrices, it doesn't matter whether you multiply by the inverse on the left or by the right, or rather on the right. Either way, you'll land back at the multiplicative identity matrix. Now, something a little bit weird is that notice that 0 does not have a multiplicative inverse. So there is no number that you could multiply by 0 in order to get to 1. So 0 is the only scalar that does not have a multiplicative inverse. In other words, division by 0 is not defined, but division by any other scalar is defined. For matrices, things are a little bit weirder. Not all matrices are what's called invertible. So a matrix that has an inverse will be called invertible, and a matrix without an inverse is going to be called singular. And you can just trust me for this first example that the matrix 0, 0, 0, 1 is singular. There's no matrix that you could multiply that by in order to get the identity matrix. So what I'm going to do is I'll tell you the procedure for finding the inverse, and this procedure will also tell us whether or not a particular matrix has an inverse. So what the procedure is in this box up here. Whoops. So the procedure says, given an n by n square matrix A, the procedure for finding A inverse is this. You create this augmented matrix. The augmented matrix is your original matrix, whose inverse you want to find, and then you augment the full identity matrix. So notice this is a little bit different from what we did in Gauss-Jordan elimination. Here, on the right side of this vertical bar, we're going to have the entire square identity matrix, not just a single column. Okay, and then what we'll do is the ordinary Gauss-Jordan elimination to reduce the augmented matrix. So we will reduce that left side matrix to the identity matrix like we normally do. And then the important thing in terms of interpreting your answer is this step 3. If the left side of the reduced form has a row of zeros, like we've sometimes seen, then the original matrix that you started with is singular. And that would mean that A inverse does not exist. But otherwise, the reduced form will be that diagonal ones matrix, which we like to see, and then some other matrix on the right side. And if you can make it to that form, then that right side matrix is going to be the inverse. So let me show you how to do this in this first example. So let's look at 5. In example 5, it says A is this 2 by 2 matrix, and we want to compute A inverse and then check our answer by computing the product A times A inverse. So notice that if you want sort of a sanity check, you can decide what you think this product should be. So what should A times A inverse be? You can pause the video if you need to think about it, or rewind a little bit. But if this really is the inverse that we're computing, this product should end up being the diagonal ones matrix, which is the multiplicative identity. Okay, so we expect the product of the 2 by 2 matrix A with its inverse to be the 2 by 2 matrix, which is the multiplicative identity. Something to notice here is that only square matrices can have inverses for a sort of technical reason. Which I unfortunately can't get into, but anytime you see a non-square matrix, there will be no matrix that you can multiply by it in order to get an identity matrix on either side. So in other words, this property up at the top, can't be held by any non-square matrix A. So we're always going to be looking for inverses of square matrices in particular. Okay, so let's go through the procedure up here to compute the inverse of A. And the way that we're going to do that is we'll take the matrix A, which is 2, 1, 1, 1, and we will augment the identity matrix on the right side. And now we're going to use Gauss-Jordan elimination to compute the inverse. And remember, the way that we're going to do that is through the usual row reduction operations on the matrix on the left. Notice that whenever we apply a row operation, though, it does apply to the entire row. So for example, if I wanted to get a 1 in this top left entry, which is usually our first step in Gauss-Jordan elimination, what I could do is maybe take row 1 minus row 2, and that would become the new row 1. So I'll take that step. So I'm going to take the top row and subtract what's beneath it. So that would result in a 1, 0. But notice we have to apply this row operation to the entire row. So on the right side of the augmentation bar, I would get a 1 and then a negative 1 because I'm taking that top row and subtracting what's beneath it. And we didn't change the bottom row here, so the bottom row is still 1, 1, 0, 1. Okay, and then we need to do one more row operation in order to finish reducing this matrix. Notice that we now have a 1 where we want it in the first column. And so in order to finish fixing the first column, which is ordinarily what we do in Gauss-Jordan elimination, I need to kill this circled entry. So I want that 1 to be a 0. There's an easy way to do that. Now that we have a leading 1 in this column, I can now just take row 2 minus what's above it, and that will be my new row 2. So if I take row 2 and subtract what's above it, this would be a 1 minus a 1, which gives me a 0 in that entry. And notice here the first row is not changing. So the only thing that's changing now is the second row, and we're taking the second row and subtracting what was above it. So this is a 1 minus a 0, which is a 1. This is a 0 minus a 1, whoops. 0 minus a 1, which would give me a negative 1 here. And then for this last entry, I'm taking this row 2 entry, which is a 1, and then subtracting a negative 1. So 1 minus negative 1 would be a positive 2. Okay. And now if you look up at step 3 in the procedure above, it says if the left side of the reduced form has a row of zeros, then A is singular. Otherwise, the reduced form is the identity matrix on the left, which is what we have, like we normally want with these Gauss-Jordan elimination problems. And then the matrix on the right is the inverse that we were looking for. So what I claim is that A inverse should just be this matrix on the right side. 1, negative 1, negative 1, 2. Okay, so we've computed A inverse, and we're going to check our answer by computing A times A inverse. So A times A inverse is going to be the matrix A that we were given, which is 2, 1, 1, 1. Times the inverse that we computed, which is 1, negative 1, negative 1, 2. Now, if you want, you can pause the video and compute this yourself. But for the 1, 1 entry, you should get a 2 minus 1, which is a 1. For the 1, 2 entry, you should get a negative 2 plus a 2, which is a 0. For the 2, 1 entry, you should get a 1 minus a 1, which is a 0. And then for the 2, 2 entry, you should get a negative 1 plus 2, which is a positive 1. And indeed, we did get back to the identity matrix like we wanted. So this gives us a way to check our answer. If you ever think you came up with an inverse to an original matrix, you can always check your answer pretty quickly by just computing the product of A times A inverse. That's supposed to get you back to the multiplicative identity, or the identity matrix. Okay. So that concludes that problem. Now, let's try to do the same thing in problem 6 here. So this matrix is 1, 1, 1, 1, and it says show that A inverse does not exist. So remember, the procedure on the previous page says that basically in all of these cases, we're going to be forming the augmented matrix where we attach the identity matrix on the right, and then we try to reduce the matrix on the left to the identity matrix. But the important thing here was this third step. So it says, if the left side has a row of zeros, then A is singular. Otherwise, you've made it to the diagonal ones matrix. So here we're going to show that the inverse does not exist. The only way that we have of doing that is just to compute the reduced form and show that that reduced form has a row of zeros. So I'll go ahead and go through the usual strategy. You may be able to immediately spot that the reduced form here should have a row of zeros, but still I'd like for you to just go through the usual strategy. So I'll append the identity matrix on the right side of this augmentation bar, and then we'll go through the usual row reduction strategy on the left side. So I have the one where I want it in the first column. My next step would be to eliminate that circled entry. To do that, I'll take row 2 and subtract what's above it. So we'll take row 2 minus row 1. That's the new row 2. Now, the first row is not changing, so I'll have that. For the second row, if I take the bottom row and subtract what's above it, I should get a 0, 0, a negative 1, 1. And now notice that here, the matrix on the left side has a row of zeros, and therefore A is singular. Or in other words, does not have an inverse. Okay, so if I ever ask you to show that some inverse does not exist, I just mean try doing this strategy that we did for the previous problem, but what you'll end up seeing is that there's a row of zeros which prevents us from getting that diagonal ones matrix which we want on the left side. Okay. So lastly, we're going to look at this problem 7. In problem 7, we're computing the inverse of a 3 by 3 matrix. Notice that this is still a square matrix, so this is still perfectly valid. I'll go ahead and write the square matrix here. Now, it's important to attach the identity matrix of the appropriate size. So if you're trying to invert a 3 by 3 matrix, you'll attach the 3 by 3 identity matrix. But we're still going to be focused on this left matrix here, and we want to reduce it to the identity, just like we normally do when we're solving systems of equations. So I have the one where I want it here. My first row operation is going to be row 2 minus row 1 in order to eliminate this entry. So we'll take row 2 minus row 1 as the new row 2. And if you'd like, you can try doing this entire problem on your own if you want to go ahead and pause the video. I'll go through this a little bit quickly, but this would be good practice for you now that you've seen how to do this in the 2 by 2 case. But if we take row 2 and subtract what's above it, we should get a 0, a negative 1, a 0, a negative 1, 1, 0. And then the bottom row didn't change. Okay, so remember, we're working on reducing this left side matrix to the identity matrix. We now have something pretty close to what we want. The new problem is that this entry is not a 1, but we can pretty easily fix that by just taking that middle row, which is row 2, and dividing it by a negative 1. So I'm just going to flip the sign of everything in that middle row. We'll get a 1, 0, 0, 1, 0, 0. And then flipping the sign of the middle row, I'll get this. And the bottom row didn't change again. Okay, so now we have the leading one where we want it in the second column. The next entry, or sorry, the next part of the procedure is to eliminate all of the other entries in that second column. So I want to eliminate that circled entry. To do that, I'll take row 3 minus row 2. That'll be the new row 3. So I'm going to take row 3 and subtract what's above it. So that means that our top 2 rows are not going to change. So I'll still have this and this. But this last row is changing. I'm taking the bottom row and subtracting what's above it. So I should get a 0, a 0, a 2, and then a negative 1, a positive 1, and a 1. Okay, and now there's one last thing that we need to do to finish reducing. To turn this entry into a 1, what we need to do is divide that row by 2. and that will finish getting that diagonal ones matrix. It will create some fractions over here, but that's totally fine. They're necessary. They belong in the inverse. So we just have to focus on this left matrix and getting it to its fully reduced form, no matter the consequences. So here we're going to take row 3 and divide it by 2. And remember, we apply this row operation to the entire row. So these top 2 rows are not changing, but the new bottom row will be 0, 0, 1, negative 1 half, 1 half, 1 half. Okay, and now we've completed the task of reducing that left side matrix. This thing on the right will be C inverse. So C inverse is equal to that matrix that lives on the right, now that we've completed that identity matrix on the left side. So C inverse, if you wanted the matrix that you would need to multiply C by in order to get to the identity, it would be this matrix. Okay, so now we've found C inverse. So that's all for the problems in this section of notes. I did want to mention sort of a nice application of this a little bit quickly. So maybe let me go back up to peek at this matrix in 5. So in 5 we had the matrix 2, 1, 1, 1. So let's say that we had this system. So we have 2x plus y equals 3, and x plus y is equal to 4, for example. Okay. So we could try solving this system in the usual way. You could think of this, though, as being a statement about matrices. You could think of this as being a 2-by-1 matrix equal to another 2-by-1 matrix. So we could think of this as saying that the matrix 2x plus y and the matrix x plus y, the entry 2x plus y and then the entry x plus y are equal respectively to the entries 3 and 4. So equality of matrices is the same thing as equality of each of their entries. So this thing over here is the same thing as this statement. Now something to notice is that you could rewrite the left side of this expression up here as the matrix A that we worked with earlier, which was 2, 1, 1, 1, times the column matrix xy. And if you'd like, you can check that by just using the ordinary rules of matrix multiplication that we saw earlier. So all 3 of these are equivalent with each other. So these are 3 different ways of writing a system of equations. But now remember, this was our matrix A from earlier. One convenient way for solving systems of equations, now that we have this technology for inverting matrices, is notice that here, if I wanted to get xy by itself, so if I wanted to isolate this column matrix, what I could do is I could essentially divide by A on both sides, which is the same thing as multiplying by A inverse on both sides. So if I take A inverse and multiply on the left by A inverse on both sides of this equation, then this A inverse will cancel with the A, and the left side will become the column matrix xy, and the right side will be A inverse times 3, 4. And you can go back to that previous problem if you actually wanted to solve this system in this way. This would give you some number and then some other number, and that would be your x and the y value that solved the original system. So this gives us sort of a shortcut, but notice that the way that we solve a system is just by row reducing the corresponding matrix to the identity. That's also, unfortunately, how we compute the inverse. So this isn't really that much of a shortcut, because in order to compute this inverse, you would have to do the same thing that we would do to solve the system ordinarily. So this isn't a huge shortcut, but this does have the benefit of being something that you could maybe tell a calculator to do. Okay, so I'll go ahead and end the video there. Feel free to email me if you have any questions, and I would be happy to help.